really first thought of giving a talk on what quasicrystals have done for me personally, but then I decided I should really talk more generally about mathematics. But they're really the same because I first learned about quasicrystals just about 2 weeks, I guess, after the announcement, maybe a month after the announcement in the publication in Physics Review. I had, as Danny said, Louis Michel and I had organized a conference on mathematical crystallography in Paris at the Institut des Hautes-Études. And this is we had people coming for a month. It was a month-long conference, all on mathematical crystallography as we understood it then, which meant higher dimensional space groups. It meant packings. It meant color symmetry. It meant various physical properties of crystals that had a lot of mathematics in them and so on. And so we had people coming from many places, and I personally thought, I'd been in that field for quite a while, and I thought to myself, this is the last thing I'm doing in this field, because it had gotten, frankly, boring beyond belief. The problems were, this is what Kuhn, Walter mentioned, or someone did, Thomas Kuhn's book on the structure of scientific revolutions. He has talks in there comparing revolutionary science and revolution to normal science. And normal science degenerates, or can degenerate, into just tweaking more little things and crossing more T's and dotting more I's. And this is where that subject had gotten, in my view. And when I got to Paris for the meeting, Louis Michel shoves the journal into my hand and said, "Have you seen this?" And I said, "No." And I read it, and I thought, oh, that's strange. You know, that's very strange. And then it turned out that Danny and Denis, of course, who lived there, and I guess John Kahn were all in Paris, and came to the meeting. And we just threw out the whole program that we had. The people who were scheduled to give talks did, but that wasn't what was really going on. And instead, it became talking about your discovery and its relation to Penrose tiles and various other aspects to it. And by the time that meeting was over, we realized that an old paradigm had crashed and a new one was emerging. We had no idea what we were talking about anymore. We had no idea. We used to think we knew what is order. We didn't know anymore. What was a crystal? Didn't know anymore. We disagreed with you that these were not crystals. They were crystals in some way. We just had to redefine crystal. And so everything changed, and it's been a really wonderful, exciting 25 years. So that's my personal thanks. But what I'd like to talk about today is what quasicrystals have done for mathematics and the gifts to mathematics as a subject, and not vice versa. So I'm not talking about what mathematics has done for quasicrystals or even quasicrystal theory. It may have done nothing in the end, but it certainly has, quasicrystals have done a lot for mathematics. So that is what I want to talk about. One of the pioneers of understanding Penrose tiles, and in fact the one who first saw them as projections from high-dimensional space, was Dick de Bruyn in Holland. And as soon as he heard about the quasicrystals, he said, "This is a gold mine for mathematics." And indeed it has become that, has been that. It was that from the very beginning. That's what we saw at that first conference. And here is about 10 years later, that was 1995, there was another month-long conference, this time on aperiodic order, mathematics of aperiodic order in Waterloo, Canada. And this is a page from the proceedings. The picture of the gold mine was not in there, but that is the others. I just wanted to mention what some of these problems are. These are all different things that were talked about there. Strange tilings, like tilings with knots in them. There were discrete Delaunay graphs, which I'll be talking about a little bit later, or at least Delaunay things. There were questions on diffraction. There were questions on local rules for tilings. It's hard to see, and even I can't see them here. But there were all kinds of different problems that were raised at that meeting and discussed then, and most of which are still being discussed today. I'm not going to talk about specific problems, though. I'm going to talk about general trends and ideas that quasicrystals, I would say, galvanized. These are things that weren't done entirely by quasicrystals, but quasicrystals were an enormous catalytic effect or galvanizer. You can't see from the top of the screen, but galvanize is to galvanize into life, to galvanize life into something, to catalyze, to increase the rate of a reaction or process by catalytic action. quasicrystals catalyze several trends and have made them, accelerated their development, and I think it's been a tremendously beneficial thing for all mathematics. So what are some of those things? The first one is restoring the gift of sight. This is the two pictures that you see here. One is of one of my children playing with mirrors and understanding mirror images. The other is Professor Coxeter, who died a few years ago, who was a leading geometer, but he was also very much in the wilderness for most of his career, because the kind of geometry he did required you to build things, build models, and to see them and look at them and think about them. And this was totally out of fashion for a good part of the 20th century, even in geometry. You would think that geometry would always be somewhat hands-on and somewhat visual, but there was a long period where it was not. And this was partly under the influence of the French, French mathematicians. This is a wonderful book called Downcast Eyes by Martin Jay, who's not a mathematician, and I'm not sure he's even aware that what he has to say relates to mathematics. But the book is about what he calls the denigration of vision in 20th century French thought. And this is mostly about philosophers and literary theory and so on. But it all does apply. I think it's wonderfully ironic that Amazon tells you to look inside a book which is about not looking at anything. But both in the philosophical aspects where vision was denigrated and in geometry, it was considered to be very bad form to even draw a picture. Everything was supposed to be extremely abstract, and a good geometer never drew pictures, never looked at pictures. And who were the criminals? This was the Bourbaki group, who made, for reasons that made sense at the time, but actually came to, I think, have a bad influence, the fierce abstraction that dominated not only French mathematics, but permeated out to everywhere else, including the United States. So Bourbaki is over. I mean, they still exist as a group, but they're not as fanatic as they were about these kinds of things. And I think that the quasicrystals made a huge difference because you have to look at them. When this picture appeared, people suddenly realized there was something here to see, to understand, and that there was a visual component to our knowledge and to our way of thinking and to all geometric thought. So that is one of the first gifts, I think, that was extraordinarily important. Another one was giving board games some gravitas. Even at the time when Martin Gardner published Penrose's two ROMs, you know, that Martin Gardner had a column in Scientific American called Mathematical Games, and that's where that appeared. It was considered a game. It was a board game. It was fun. There were a few other tiles came along, but nobody took them really seriously until quasicrystals were discovered. Then suddenly it was realized these were not just a board game that you could play with in the back room. This was something you could really study and think about. And so on the right-hand side, this one I grabbed from the internet. This is a picture of interactive, I think, board game that has to do with five-fold structure that you can play with. Now there is this marvelous online tiling encyclopedia that I recommend everybody go to and play with. This is at the University of Bielefeld, and these are just a few of hundreds of tilings that have been studied and generated in the last 25 years. Most of those were never thought of before Danny's discovery. Some of them were, of course, the Penrose tiles were, and the octagonal tiling, but most were not. But he galvanized the interest in thinking about what kinds of shapes can tile a plane and aperiodically, non-periodically, and what kinds of properties do they have, and do they all have diffraction patterns with bright spots, or do they some not? And what do we mean by order? And all these questions are raised in the study of these tilings. So I strongly recommend everybody go to that website and play with it. Then he asked a little earlier about the term aperiodic order, and I forgot to address that. I'm not sure. It certainly was used, I think, at that workshop, or aperiodic crystals. It was used, and whether it was Louis Michel who first said it, it could have been, as he was extremely clever and thought of many good ways to say things. But it may have just somehow burbled up from the group. But I think it probably did start there. And then it was. There was also quasicrystals has also brought about one play that was off Broadway called Delicious Rivers, which is a strange title, and I won't explain where it comes from. But the play was about Penrose tunneling, quasicrystals, and particularly the main character was Robert Ammon, who had also discovered what we call Penrose tunneling. And this played for a week in New York off Broadway, and then it played at Smith College, and it's a music comedy. So I'm sorry that the videos turned out so badly, or I would have shown you some of the scenes from it. So anyway, there has been also levitas as well as gravitas. Another thing that quasicrystals have done for mathematics, which I personally think is extremely important, is to demote the role of group theory in geometry. Again, not only by no means entirely due to Bourbaki, but it was the trend for 100 years in geometry had been to consider geometry as group theory and nothing else. And that came about through crystallography in strange ways. This is a picture of one of the earliest what we could now consider as crystallographic drawings up there, as crystal structure drawings, but I can't pronounce his name. It's Aoi, who first proposed in detail the modular structure of crystal growth and tried to show through these pictures that he drew up there how you could build with the same building blocks something like a pyrite structure or like fluorite structure, depending on how you finish off the stack. So this was his early effort to show what crystal structure probably was like, and it was 1822. And in crystallography, the story goes this way, that he proposed that structure. His students felt that the blocks were too complex. Nobody knew what they really were. This was before people thought about atoms very clearly, and replaced them with points. And then that led to Brave's discovery or enumeration of the 14 lattices. And then once that was in place, then was just a matter of time, but it took some time before X-ray diffraction revealed that, in fact, yes, crystals were lattices. And this famous picture here of showing one of the first pictures of diffraction from a lattice. So that is a crystallographic story, but for mathematicians, that's not the way the story goes, not quite. It goes differently. First, before I say that, I want to show this slide, which is 1918. It was another birthday party. This was for Aoi, and he was 175, so he wasn't able to be there for that. But this is the menu from the dinner, which I thought was glorious. Whale steak, among other things. And this was held in New York at the American Museum of Natural History. And you might ask why 175th birthday in 1918 was such a lavish thing. And this, of course, is because X-ray diffraction had been discovered a few years before, and this was celebrating the triumph of his vision of the crystal as lattices of building blocks. So anyway, for mathematicians, the story's a little different. Bravais was one of the founders of group theory from a mathematical point of view. He did many things, and he only did this for a little while, but what he did was very seminal. He not only enumerated the lattices, he also enumerated the groups of rotations and symmetries of the sphere. And he did it in a very sophisticated way. And this was just at the time of group theory with Galois and so on, and his work was very influential on later mathematicians. And then came along Felix Klein with his Erlangen program, which declared that we should study all geometry through the groups of transformations that leave that geometry invariant. Klein was not thinking about crystals necessarily, although he was aware of Bravais' work, but he was also thinking about the problems of understanding Euclidean and non-Euclidean geometry and how to distinguish between them. And he made this declaration or this program that we look at the groups of transformations, and that's what geometry is. And that, for mathematicians, is what geometry became. Simply group theory. And everything else that could not fit into that paradigm was just ignored. Hilbert was arguably one of the greatest mathematicians of the 20th century, and in 1900 he gave a very famous list of problems, 23 problems, to guide mathematics in the next century. And his 18th problem was called Building Up Space from Congruent Polyhedra, but mostly the first part of that problem was developing the space groups, these groups further. These 230 space groups had been enumerated now, and now he said, let's talk about higher dimensions. Are there finite number in higher dimensions, and what can we know about them? And that was his 18th problem, and it turned out, yes, there are only a finite number in high dimensions, but it put the focus on the groups, as you see, not on the polyhedra themselves. And actually, this is nice. In 1978, the four-dimensional crystallographic groups were actually enumerated. There are several, 4,000 or something like that. And I got an email just the other day from Peter Engel, who's still working on this, that in 6 dimensions he's got 200 million different types of polyhedra that fill space in a periodic way and thus in a group way. So I don't know if he's going up to 7 dimensions, but anyway, that work is still going on. But Hilbert understood that groups aren't everything and maybe not even the main thing. And so part of his problem, which he just added on at the end as an afterthought, was that it's important to number theory, also maybe to physics and chemistry. How can one arrange most densely in space infinite number of given solids, spheres with a given radius, or tetrahedra with given edges? The spheres, the most dense packing is the one that Walter just showed you before, but that was conjectured by Kepler and only proved 300 years later, which just a few years ago. The question of packing tetrahedra is still unsolved, and this is one that's a very, very hot problem today, and literally every week or every other week there's a new publication about this, and one of the leaders in this field is Veit Elser, who played a big role in quasicrystal theory early on. But anyway, even though Hilbert had raised this question, people did not pay attention to it until quasicrystals were discovered, because you really had to smash the paradigm to be able to think constructively about packings in space and so on. So you really did demote group theory from people's thinking and make them realize to think more broadly, more generally, and to look at things that did not fit there. So thank you for that. Another gift to mathematics is finding something for the n-dimensional lattices and space groups to do. They were there, and people had found them, but what do you do with them? There was earlier work by Minkowski, by Voronoi, Coxeter, Mier, Janner and Janssen, and others. And this synthesized them, that brought them together, and people could see, oh, we do have a theory of high-dimensional lattices and space groups, and we can subsume many things into that, and that became the cut and project method, or the high-dimensional projection method that Walter talked about, which yield an astonishing variety of non-periodic tilings and point sets, integrates all that early work together, and that's always a plus in mathematics, and became a tool for classification and description. And I've always been rather lukewarm, shall we say, to this high-dimensional approach, because of the words of Professor Kitagorodski in Russia, who said, a first-rate theory predicts, a second-rate theory forbids, and a third-rate theory explains after the fact. And this always seemed to me to do a lot of explaining, maybe some forbidding, not too much, and very little predicting. And so I've been a critic of this for a long time, until today, because Walter's persuaded me that it is actually more than just useful, that you really can get a lot of information from this, and it's not just, it is a descriptive tool primarily, and it's a way of relating different structures together and seeing how they interact and how you can move from one to another and seeing the diffraction pattern, but it's more than I thought. So thank you. I hope we'll all learn things today, but I've certainly learned already. But nevertheless, I think we should keep this in mind because it is a description. It's just an extremely useful description. Another gift that I think is extraordinarily important is rediscovering the Boris Nikolaevich Delaunay, who was a Russian mathematician who had a deep interest in crystallography. He lived for 90 years, from 1890 to 1980, and his work was well known in Russia and much appreciated there, but not well known outside. And this, the discovery of quasicrystals forced people to think about his work and use it in more and new creative ways. And I think that rediscovering Delaunay was an extraordinarily important thing. What did he do? Back in 1930s, in 1934, he and Podurov, who was a crystallographer, and Alexandrov, another mathematician, decided to look at crystals as points, just the way you do when you consider the lattices, crystals, atoms as points, but not to presuppose any structure at all. and to start with nothing and see what it takes to build up. So he proposed simply two postulates. One of them was that there's the points that you consider point sets, there's a minimum distance between them. And that's what he called his little r here. So this is the minimum distance between 2 points. No 2 points can be closer than that. He thought that made sense from a physical point of view. And also that there were no arbitrarily large regions with no points in them, so that there would be a maximum radius for what he called an empty hole. And with those two postulates, a lot follows. It's quite amazing how much you can get from that. And that is what this book is about, the mathematical foundations of the structures of structural analysis of crystals, starting just from these axioms and building up. And Delaunay and his students worked on this for many, many years. And in 1976, they were able to prove that this kind of local regularity, local clusters, all being the same, implied global regularity. So what they did was they considered for each of the points in their system, which there are infinitely many, but here's one related to draw the lines with all the other points. They called that the hedgehog. And then they were able to prove that for every such set, every Delaunay set, there is a radius such that if all the stars, I'm getting the wrong thing. All the stars are congruent, then it's a regular system of points. It's a crystallographic group. It can be described by a crystallographic group. So that building up from just, and this is these radii are very small, so that you could draw a circle around every point, and if what you saw inside was the same for each one, if all the clusters with finite radius were the same, then the whole thing had to be periodic and regular and so on. This was amazing, actually, that they could do that. And so it turned the whole thing upside down. Instead of saying, let's start with a lattice and put things on it and so on, let's just start with this loosely defined thing and then see what structure we can build. And it turns out, and I completely agree with it, Delaunay sets are the natural formalism for quasicrystal models from a mathematical point of view. And you can classify them in many, many different ways. Here's one hierarchy of these kinds of sets. It's just a general one that could describe a gas as well as a crystal. Finitely generated. I won't go into what this all means because these are technical terms, but they're all defined in terms of the different sets of the directions between the points, which essentially is in terms of these stars. If there's a finite number of different stars, the model set, these are the ones that are projected from high dimensions. These are not necessarily, or if they are, it's more complicated. Then this is a periodic set, and this is a lattice. So you have a gradation of increasing restrictions on these, which build up from a gas to a lattice in a natural way. And this is primarily work done by Ligarius, but other people working with him. And it's a very beautiful and elegant way of classifying point sets in trying to understand aperiodic order. And this relates to the diffraction patterns, so this is a very natural also correspondence. Now, one question that I think is a very important one is whether there are local theorems for aperiodic Delaunay sets. And I don't think this has been studied very much, if at all, but could be a very nice way of tying his local approach into the more closely into the study of aperiodic point sets. Then, if we put all this together and more, we get something called a whole new field, the field of aperiodic order. And this is a field that didn't exist before. This is a gift of quasicrystals to mathematics. It's a very active field. It involves all the things I've been talking about and more, and has people working in it from all over the world. They're mostly mathematicians, but also many physicists are involved with this. And this is sort of the fruit of the gold mine, or the yield of the gold mine. This field attempts to put all the pieces back together again, all the pieces that we've been talking about, into a coherent whole that makes some sense. So here's one way of thinking about it, if you like Venn diagrams. The different topics that come up in studying aperiodic tilings and point sets and so on, the matching rules for tiles, self-similar tilings, which Walter mentioned, which were subsumed under dynamical systems, local complexity, which has to do with the number of these small little stars, diffraction patterns, projections from high dimensions. How are all these things related to one another? if you look at the Bielefeld website, you'll see that some of these tilings have some of these properties and some have others, and some, very few, have them all. Penrose Tilings has everything. What else is in here? This was one of the first questions that was addressed in this field, is what's going on in here? What has everything? What is the most rigorous, I wouldn't say rigorous, but most orderly type of aperiodic order that there can be? And that would be the intersection of all these questions. Which tilings, for example, have matching rules and bright sharp spots and finite complexity and are self-similar and are projected from n-dimensional lattices? The Commission on Aperiodic Crystals that defined a crystal, that Walter also mentioned, crystal was defined to be any solid having an essentially discrete diffraction diagram. This did not mean, as I understood it, I was on that commission too, that it meant only bright spots, that it could also have a diffuse background, possibly, but it had to have the bright spots. And this definition posed a problem, and it was designed to pose a problem. As Walter said, it's not a definition that says this is what a crystal is exactly. It says it's phenomenological. It says if there are the bright spots, then it's a crystal. But that didn't say what has bright spots. You know, what kinds of sets have that? And that was the problem. We didn't know. So anyway, there's that picture. So determine which Delaunay sets, that was the problem, correspond to which combinations of diffraction measures. By combinations, I mean, from a mathematical point of view, a diffraction is a measure, and it can be a sum of three measures, a pure point or Bragg measure, singular continuous, as Walter said, and absolutely continuous. And some sets are purely Bragg points, and some are purely absolutely continuous, and some are mixtures of these. And we all assumed, or at least I certainly did, and I thought we all did, that we would be able to tell that the different types of point sets would line up in some way. We'd be able to classify them by some combination of these measures, and that was the program. That then once we had done that, we could say what is a crystal in terms of where are the points, as opposed to just the diffraction pattern. But I don't think that's going to happen because strange things are happening, are being found. And this is one of the strangest, is that there is a one-dimensional sequence. This is not Fibonacci. It's much less orderly. But which is the Rudin-Shapiro sequence, which is also given by a recursion rule, and it gives you a series of ones and zeros, and that diffraction, that sequence has exactly the same diffraction pattern as a random coin toss, and this defies all logic and certainly all intuition that something deterministic like a recursion sequence and something random like a coin toss should show up the same way. These are not the bright spots, these are diffuse, but nevertheless it just shows that diffraction is not going to do that. And so it makes me wonder in terms of what it really is, how are we going to define aperiodic order? What are the right ways to look at it? And so if we look back at the Venn diagrams, we see that the real questions are not in the center, because we know what's there pretty much, but what's out here? You know, what kinds of orderly structures do we have in these hinterlands that are in parts of these and not all of them? And I find that that's where some of the really exciting work is being done at this point. And that in 1900 was when Hilbert gave his list of 23 problems. In 2000, lots of people vied to come up with another list of 23 problems, of course. And some of them were interesting and some of them were not. But this particular list was put out by DARPA, as the DARPA is the defense agency that funds big bucks to mathematics and to others. And they came up with a list of 23 problems that they said were critical to the defense of the United States. Among these are the Riemann hypothesis and other problems that are hard to see what is the connection. And so I asked Benjamin Mann, could you tell me how the Riemann hypothesis, settling that, will defend the United States? He said, leave that to me. And what he meant was, I'll get you the money, you do the math, and we'll get the money, and don't you worry about that. So anyway, this one, however, may mean something. This is his 11th problem, not the 18th, but it's very similar to Hilbert's 18th. It's optimal nanostructures. It's just new language. Develop new mathematics for constructing optimal globally symmetric structures by following simple local rules by the process of nanoscale self-assembly. And if you look at that closely, you realize that except for the and, by, there's not one word that we understand. And I think quasicrystals, one of the great gifts is to show how hard this problem is and how much work we have to do to make sense of it. So closing with the end of that, and just listing some of the problems that I'd mentioned: the gold mine, restoring the gift of sight, giving board games gravitas, demoting group theory at last, finding work for the ND lattices, rediscovering Delaunay, and creating a whole new field. I think that's a lot. And so thank you, Danny. And